Hello everyone, this is Dr. Hopkins with our next in our series of videos about general chemistry. And in this one we're going to talk about or continue discussing the structure of atoms with respect to kind of electronic structure. Where are the electrons located outside of the nucleus? And so as I said, we know from previous discussions that atomic structure has a nucleus surrounded by electrons outside of them. Most of the properties we're interested in are electronically based. So in other words, the locations and the energies of the electrons of the atom are what dictate the properties that we care about. So things like size, whether it's a metal or non-metal, whether it forms ionic or molecular compounds, and any of the other periodic properties we'll talk about in this class. So let's talk about how we define where the electrons are. Okay, so we're going to classify electron locations and energies as what we call orbitals. Now remember, electrons, as we established in the de Broglie wavelength discussion, is electrons are matter, they can act like waves, so we really can't locate them very well. So this idea of location is really more like a probability, okay? So our orbitals are these regions of, excuse me, where it's most probable to find that electron. And we define our orbitals using a set of quantum numbers, and we're going to have 4 of them. Let's start with the first one, is the principal quantum number, and that's the one we've already discussed. We did the Bohr model before, where it had n equals 1, n equals 2, and so forth, the electron around the hydrogen atom. And it's basically, let's see if this is all right. It tells us our distance from the nucleus, okay? And then the second quantum number is the angular momentum quantum number. It's going to be L. Okay, and this is how the electrons move around the nucleus. What kind of shape do they take, how fast they're moving, and so forth. And then we have the magnetic quantum number, m sub L, and it's with respect to, so it's called a magnetic quantum number because the orientation of the orbital matters, or the orientation of the orbital, it reflects the orientation of the orbital, and it's magnetic because it would respond differently in a magnetic field depending on the orientation, okay? And so that's just the reason why we call it a magnetic quantum number. Later on, we'll talk about a little more practical consequences, excuse me. And then the last one is a spin quantum number. Actually, this one is irrelevant whether it's an orbital or not. Just an electron flying through space has spin. It's a property of spin of electrons, and then basically they also respond to a magnetic field. Either they will reflect up or down depending on their spin. Okay, so let's go through each of these quantum numbers. So the first one is the principal quantum number n, and it can have any integral value. So this is all the way up to infinity, although we almost never occupy an infinite quantum number state. And it relates to how far the electron is from the nucleus. So if we use the kind of, the old Bohr model, remember we had n equals 1, and then you go out, n equals 2. Well, now they're not necessarily the circular orbits, but the farther, so n equals 1 is the closest, and then they kind of go up as you go along. So if you have an electron at n equals 3, generally is farther away from the nucleus than an electron that's n equals 2, or n equals 1. And then our angular momentum quantum number, L. Now L, its values are restricted based on which principal quantum number it's in. So L can be equal to 0, 1, any integer value, all the way up to n minus 1. So if we had an n equals 0, n equals 1, then you can't have n equals 0, it's not on the list. L is equal to 0, and there's no other possibilities. If we have an n equals 2, L can be 0, because that's always a possibility, and then 1, because 2 minus 1 is 1. And those are our only possibilities of L. But in general, depending on how high your n, you can get large values of L. So this relates, as we said before, to the shape of the orbital. So if we have L equals 0, we typically call it an s orbital, okay? And they're spherical. Okay, so you would just have, this is a circle, but imagine that's in 3 dimensions. It's spherical. all s orbitals are spherical in shape. So the probability is kind of this sphere. L equals 1. So if we have an L equals 1, we usually don't say L equals 1. We usually call it a p orbital. Okay, so here you have s orbitals and p orbitals, and they're dumbbell shape. So you have something like that, or like a figure 8, depending on how you write it, right? So you'll have two lobes. One lobe will be a different size, sign, or phase. So it could be plus, minus, or shaded. But that's what those look like. Then if we have L equals 2, those are d orbitals. They tend to be clover leaf. So we have then 4 lobes. And then we would shade these different phases, and we'll talk about how many there are of each one of those. L equals 3 are the f orbitals. I'm not going to draw those. They just add more and more lobes. L equals 4 would theoretically be a g orbital, but there are no g orbitals in the periodic table, so we haven't observed one of those yet, so we don't really know what the shape would be. But it would just add more and more lobes around the nucleus. All right. Now then we have our magnetic quantum number, m sub L, and it basically just tells you the number of orbitals, so of that particular L value. So the m sub L can be anything from minus L at an integral value all the way up to L plus L. So if we have L equals 0, the only one value of m sub L is 0. So that means if we have an s orbital, there are only one s orbital. There's only one of the s orbital, okay? If we have a p orbital, right, so here's L equals 1, then we have m sub L can be minus 1, 0, and 1. That means there are 3 p orbitals. Okay, so that's what I mean by it telling you how many orbitals that you have. The d orbitals, that means there are 5 d orbitals, and then there are actually 7 f orbitals if we were to go through that process all the way. Okay, so our s, we would have some n value. We'll have L equals 0. We'll have m sub L equals 0. So we would just have one sphere, right? So whatever that might be, that doesn't really matter. P, like it says, we have 3 p orbitals. We have m sub L equals minus 1, 0, and 1. Typically, we would draw these as not exactly the same. So we might have one in the x direction. We'll write one in the y direction. And then, if I can draw it kind of coming out of the screen here, in the z direction, right? So you have a lobe pointing along the x, y, and z axes. And then the d, we have 5 of these. I'm not going to draw all of them, but you basically have 4 of them that are these clover leaf with various levels of various, in various directions, xy, in the xy plane, the yz plane, the xz plane, and so forth. And then there is the last orbital you have looks like a p orbital with a hula hoop around it. Okay, it's got this kind of circle around that, and that's a different shade. And so those are, you have 4 clover leaves and that one really odd p orbital with a hula hoop around it. And those are the shapes of your orbitals that you have. And then the last one, the last of the quantum numbers is our spin quantum number. The property called spin. Now we're going to give it m sub s is going to be the abbreviation for it, and it can have a value of plus 1/2 or minus 1/2, and that's spin up. So plus 1/2 we tend to say spin up, minus 1/2 tend to say spin down. Sometimes we can represent these as arrows. So spin up would be a half arrow that way, and spin down is a half arrow that way. And that's one way to represent electronic spin. All right, so let's put these together. If we have an electron, we have 4 quantum numbers. Each electron has a unique set of 4 quantum numbers. So no 2 electrons can have same quantum numbers. And what I mean is no two electrons in an atom. Obviously, if we had two different atoms, they can have electrons with the same one. So we have no two electrons have the same quantum numbers. This also means that because of the spin value, m sub s plus half, m sub s minus 1/2, we can only have 2 electrons per orbital. So our m sub l tells us how many orbitals we have. Our spin tells us how many electrons we can have per orbital. And also the values that we have. So remember, n equals 1, any kind of integral value from 1 all the way up. L can be from 0 to n minus 1. That means that we can have a 1s orbital, so n equals 1, L equals 0, but we can't have a 1p orbital. We can't have n equals 1, L equals 1. That's not an allowed orbital. And so we can go ahead and write the possible quantum numbers for, say, a 1s orbital. So it would be n equals 1, L equals 0, m sub L equals 0, m sub s is equal to plus, and I'm just going to write it in one line, plus or minus 1/2. So we have 2 possible electrons in a 1s orbital, and one will have 1, 0, 0, 1/2, and the other one will have 1, 0, 0, minus 1/2. You could do the same thing for 2p. So it already tells us that's n equals 2, right? Because this is the n right there. And then p tells us this is L equals 1. And then m sub L is equal to minus 1, 0, and 1. Because we know that's always the case for the L or the p orbitals. We have 3 p orbitals. And in each one of those orbitals, we can have 2 electrons, one with a plus half and one with a minus half spin quantum number. Same thing. 4d, n equals 4, L equals 2, m sub L equals minus 2, minus 1, 0, 1, 2, but the m sub s is always plus or minus 1/2. So you get the picture when you say, well, we'll say, well, we got a 4d electron, right? We know n equals 4, L equals 2, and then we know its m sub L can be in one of the 5 orbitals and have one of the 2 spin states. So this is the kind of summary of the video itself. It's been quite long, but all our properties are due to electrons. We've described quantum numbers that describe our orbitals, and the spin quantum number gives us only 2 electrons per orbital, which we're going to use the next time when we start coming up with electronic configurations of atoms. So until next time.